Hello, and welcome to Start All the Way Down, building fast and highly concurrent databases on modern hardware. My name is Avishai. Shalom. I'm the developer advocate at ScyllaDB. ScyllaDB is a company that makes the open source database Scylla. You can find me on Twitter as Nukenberg. That's my nick. That's also my nick on GitHub and other places. So before we begin, a little bit about ScyllaDB. ScyllaDB, as I've mentioned, is the company that makes the open source real-time big data database, online, transactional, distributed, blah, blah, blah. It's a drop-in replacement database. Drop-in replacement meaning it's compatible with Apache Cassandra and also DynamoDB. We have compatible APIs with both. But it does provide about 10 times the performance of Cassandra and with very, very low latency, especially on the high percentiles, so the long tail. It's open source. We also have Enterprise Edition. We also have a cloud service to run your own, to run database as a service, like managed database if you want. The company was founded by the creator of the KVM hypervisor, which is the main hypervisor used on all the cloud providers these days. So a very interesting project. Look it up on GitHub. It's open source. And I'm here to talk to you today about the architecture behind this database and why and what makes it so fast. So before we begin, I would like to take a look at a scalability model known as the universal scalability law. And this is the reason it's called the universal, because it's basically a model that assumes very little and it applies to almost anything. So when you start scaling systems, meaning you add resources or you increase the load on the system, initially you see linear growth in system throughput, meaning linear scalability. But at some point, the growth or the scaling becomes less than linear, or you get diminishing returns, if you will. And the reason for that is because you have some shared resource and you queue on that shared resource. So even if you add more let's say CPU cores or whatever, or machines, they can't be fully utilized. And this is known as Amdahl's law, which basically says that the overall processing of the system is limited by the serial part. You always have a parallel part and a serial part. But after this point, you start seeing negative returns. So actually the system goes and becomes slower and slower as you add more cores or more machines. And the reason for that is the need for coherency. You need to synchronize caches, for example, or you need to reach some consensus and some shared decision by all the parties involved. And this is the case, for example, with strong consistency algorithms like Paxos and Raft. And this is the reason why the clusters of Paxos and Raft are usually very, very small. They're rarely scaled beyond 7 machines or so for this reason, because when you add more and more machines, they actually become slower and slower and slower. So it's the opposite of horizontal scale, if you will. Just keep this in mind. So from here, let's talk about how databases have been built traditionally. We're going to go through the basic architecture of MySQL and Postgres, but most of the other databases out there are built in a very, very similar way. So this is the basic architecture of a database like MySQL. You have clients connecting, and each client has a connection, usually a TCP connection, and on the database side, you have a thread per client or per connection, or a process per client if it's Postgres. Postgres has a process per client. And those threads would communicate with the client and also execute the query. So they have the query parser, they have the query cache, and all kinds of stuff like that. They have their own buffers for sorting and stuff like this. And they communicate with a different thread pool, which is in charge of the storage engine. This is the IO threads. So in InnoDB, you would have InnoDB IO threads. And they're in charge of taking care of the storage, and they're in charge of updating the storage or the indexes and so on. And they actually communicate with the disk. But it's a different thread pool, and they share memory between themselves. For example, they share the cache, so the buffer pool cache for IMDb, and they would share it, and they would synchronize between themselves whenever they have to talk to the disk, or lock an index for update, because you don't want them stepping on each other. And they will also have to lock when they, for example, touch a shared cache, like the buffer pool cache. So that's the basic architecture. And the problem with this kind of architecture, which is known as the standard shared memory architecture, is that all the threads have to lock to touch a shared resource. And those locks are actually what causes queuing. So usually you would use something like a mutex or futex. Futex, if you don't know what that is a fast user space lock. Mutex is a kernel lock, but it's basically the same thing. And also you have another problem where you don't have CPU core locality. So the threads can move between cores freely, and this is basically the responsibility of the operating system to locate them on whatever core it deems vacant or ideal at the time. So to understand why this kind of architecture has now become a problem, we should take a look at what happened in the last 20 years in terms of hardware evolution. So we're going to go really quick through about 20 years of hardware evolution. So bear with me. This is a graph of RAM prices by year. And as you can see, it's exponentially dropping. I actually have data from the 50s, but if I put the data from the 50s on the screen, you won't even see this tiny notch here because it's exponentially dropping. So as you can see, like the last part of the graph is like very close to zero. And you can enlarge it and enlarge it, it's going to look the same. And the same thing happens with RAM size. So if we look at size, we see the exponential growth in the size. So we're getting a lot more RAM for a lot less money. And this is a similar graph, but not in terms of prices, but in terms of performance, but for CPU. And for CPU, the picture is a little bit more complicated. So you actually see, this is a log-scaled graph. So what looks like a linear growth is actually exponential growth. And you see that there's exponential growth in the number of transistors. This is known as Moore's law, meaning that the number of transistors is roughly doubled every year and a half. But the single thread performance has peaked around 2010, more or less, and since about 2014, it doesn't rise anymore. It's actually at a standstill, and also the frequency of cores. And the reason for that is that at some point, if you increase the frequency too much, then the silicon melts. So we're actually at the physical limit of how much we can scale a single core. And what we do instead, we just add more and more cores. So if you look at the black graph on the bottom, you see that we start to get exponential rise in the number of cores, whereas the single thread performance or the single core performance is actually plateaued. So to summarize the changes that we had in the last 20 years, we are getting more and more cores, but CPUs are not getting any faster, not a single core anyway. RAM has increased by a factor of about 1,000. Disk space has increased by a factor of about 1,000. The seek time of disks has dropped dramatically from milliseconds to microseconds. So again, about a factor of 1,000. Disks today are a lot faster. The bandwidth roughly remained the same. The throughput of network has increased about 100-fold. So again, but in this case, the picture is different from disk. So latency remained more or less the same, a little bit faster, but throughput has risen dramatically. So just to give you an idea of what's available today, the largest machine on Amazon currently has about 224 cores and 24 terabytes of RAM. That's not a mistake, that's terabytes. And you have a lot of other machines which are smaller, which have 1 terabyte, 2 terabytes of RAM. It's not a problem anymore. So what do we do with this hardware? So if you remember the universal scalability law, this is an example of what happens in the real world when you try to run something like MySQL on so many cores. And you can see that when you add more and more threads and more CPU cores, actually, you start to get diminishing returns, and at some point it slows down even. So they actually made improvements from version 5.6 to 5.7, so you can actually utilize the cores better, but the picture is not going to change dramatically. When you add more and more cores, you're not going to get more and more performance. So that's kind of a problem, really. Why is that? There are a few reasons for that. So first of all, we mentioned queuing and contention, but also we should talk about context switching. So context switching is when we move from user space to kernel space, so the kernel has to change tasks, and it has to evict one thread from the CPU and schedule another thread to do something else. And there's a cost associated with that, because you have to checkpoint some data structures, and you have to evict the caches and clear them and load different data into memory, into the registers of the CPU, and that takes time. How much time? At context switch is in the order of magnitude of microseconds. So if you remember what we said about disk speed, disk sake is also now in the order of magnitude of microseconds. So roughly about every 10 context switches is one missed opportunity to read from disk. And that's expensive when we're talking about databases. And of course, locks. Locks mean that the CPU cores are basically sitting idle and doing nothing, and you're just wasting CPU time you could have used for query processing and other stuff. And why do we have this? Because of shared memory. If you share memory, then you have to synchronize with locks, and you have to do a lot of context switching to switch between threads, and that's just the reality of this architecture. Now, modern CPUs don't actually have like a giant pool of RAM that they all talk to. That would be very inefficient, and instead we have an architecture known as NUMA. NUMA is short for non-uniform memory access, and the idea is that each physical core has its own memory, each physical CPU that might have a few cores has its own memory controller and its own local memory zone. And when it talks to its local memory zone, it doesn't have to synchronize with anyone, doesn't have to lock anything, so access to that local region is much faster. But if for some reason it has to access a remote zone that is foreign to it and is controlled by another processor, then access to that zone would actually be slower than access to the local zone. So this is why it's called non-uniform, because you have different speeds for accessing different parts of memory. And that's kind of a problem, because when you're talking about the shared memory architecture of software, you don't actually have this kind of memory locality. Threads can move between cores, and they can actually move to a different CPU, and then they lose their memory locality for the memory stored in the NUMA region. So Linux actually tries to optimize for that, but it's not always doable if the software that is running on Linux has not been built specifically for NUMA. So we also have this CPU RAM gap, where CPUs are becoming more and more and have become faster and faster and faster, but memory did not keep up that much. So bandwidth has grown, but only slightly, and also the latency of access from CPU to memory hasn't grown that much. So now, especially when we have fast disks, this has become a huge problem, because if the CPU is starved for data, and then just spinning and doing nothing and has to wait. And that's a problem, wasting a lot of resources this way. So in order to utilize all this hardware, we need to rethink how we build databases. So if we start from first principles and we rethink, knowing what we know now about hardware, how would we build a database to use all those resources? So we want to avoid locks as much as possible, and that means we want to avoid shared memory. And also we want to be able to use NUMA. So again, another reason to avoid shared memory. We want as little or no coordination as possible. And of course, no synchronization, in order to be able to get the linear scalability region of the USL as far as possible. We also want to do as little or no context switches at all, if possible, because every 10 context switches basically means a missed opportunity to read from disk. And again, because of the CPU and RAM storage gap, we want to do a minimum amount of memory copies, because memory copies basically mean that the CPU is going to wait for data to be copied, and there's really no point. We just want to process it, if possible, not even load it to the CPU. So the architecture that Scylla came up with is known as a shard per core architecture. So on the left-hand side, you see a bunch of dogs from the shared ball. This is basically a good analogy for the shared memory architecture. And on the other side, you see what a shard per core would look like, where every shard or every thread would have its own dedicated pool of resources, and they don't interact with each other. So that's the general idea. How do we do this? We need to shard the data. Each core needs to handle its own independent set of data. And this is luckily a common concept in distributed databases. And because Scylla is by design a distributed database, so it plays very nicely with this concept. So basically, we just treat the machine itself as a bunch of individual cores or a bunch of distributed systems inside one local server. So the idea is that every row has a partition key, and you take that partition key and you hash it, and then you take a modulo of that hash, and this basically gives you a partition number. And those partition numbers can be assigned on a ring, and every node on that ring would handle a specific range of partitions. And that's basically the idea. And this is how we distribute data inside a cluster of Scylla nodes, and also how we distribute it inside one server to different cores. So the problem with this kind of architecture is that data or load might be unbalanced between different partitions. Overall, if you have enough statistical distribution, then it should be fine, and we aim for uniform distribution of data if possible. But this is like, sometimes it's impossible, but it's a fact of life of distributed databases, so we have to deal with this anyway. It can be mitigated to some degree by having a layer of mapping between logical partitions and physical partitions which reside on shards. It's a topic for a whole different presentation. If you're interested in that, look for vNodes or tablets online. So Seastar is a framework on top of which Scylla is built. It's an open source framework that's powering Scylla database that I'm talking about, but also other projects like Red Panda, which is a Kafka clone, and ValueStore, which is a Memcache clone. And it's basically a mini operating system in user space. I'll talk about that in a bit. It has its own task scheduler for CPU tasks, its own IO scheduler for data tasks, and it's fully asynchronous and uses the user space coroutines or promises instead of threads, and therefore avoiding the kernel managing the threads and deciding where to put tasks and potentially move them between cores. It's using direct IO, so it completely bypasses the page cache. We'll talk about it in a bit, and it manages the cache on its own. And this means we can have one thread that's running on every core, one kernel thread, or in this case a Seastar thread, it's the same, which will be pinned to a specific core. And on the bottom you see the results of this. We actually get linear scalability when we add more and more cores. Performance just rises linearly with the addition of resources. So that's a great success. So the architecture looks something like this. Every Seastar core has its own thread that's running on that specific core, and it's completely identical to all the others. It has a task scheduler that manages the internal tasks of Scylla and also talks directly to the resources, so the network interface card, the disk, and everything else. And this is, if you compare it to a traditional architecture where the kernel manages the scheduler and the memory and everything else, then you might have a problem because the kernel basically is allowed to move tasks between different cores and destroy your memory locality. Whereas when Seastar manages it, it doesn't ever move tasks between cores. So one of the problems of running on Linux is that if you're using the Linux page cache or the networking layer of Linux, then the kernel itself has internal kernel threads that might destroy your memory locality. So the Linux page cache, for example, is shared between all the processes and all the threads, and it's not NUMA friendly, unfortunately, because different processes or different threads might be running on different cores, and also the kernel is free to move the threads between cores. So this is what happens in Cassandra, for example, and Cassandra has its own application-specific caches for keys and rows and stuff like that, which are on-hip or off-hip because it's written in JVM. And the reason I'm comparing Scylla with Cassandra is because the architecture is similar. And if you look inside of the kernel, what happens when you get a page fault, meaning that you look for data and it's not in RAM, then what would happen is that you would get a context switch, and the kernel would suspend your thread momentarily and then read from disk. And when it's done reading from disk, then it would resume your application thread. But in the meantime, it's free to run other threads on that core. So you might be resumed on a different core even. and you don't have control of this. And this is a big problem for things like Scylla, because first of all, we don't ever want to move between cores. And second, remember, if we did a context switch, we missed an opportunity to read from disk or write to disk. So what Scylla does instead is it has its own cache. It completely bypasses the Linux page cache by using direct I/O. And this allows it to have its own I/O scheduler and to have its own managed cache. So Scylla basically takes over the RAM of the entire machine. And this is why we call it an operating system in user space, because it manages the memory, it manages the I/O, it manages the CPUs, it basically does everything. So in conclusion, in order to fully utilize the hardware that has gone through a lot of changes in the last 20 years, we need to understand that software is now the bottleneck of most of the things that we use now. And if we want to fully utilize the hardware, we need a different software architecture that's basically a distributed system even within a single server. So thank you very much, and if you have any questions, I'm going to be online on the chat, and also you can reach me on Twitter, Nuckenberg, or email nuckenberg@scalability.com. Thank you.